We're going to do a quick video about balancing a redox reaction. Now this is the very simple version of looking at a reaction and seeing that it is balanced by mass. However, it is not balanced by charge. If you see that the reactant side here has a charge of 0 and a charge of 0, so the net charge on the left side is 0. Now this is a charge of +1, and there are 2 negative charges here. So the net charge over here is actually a -1. 1 plus -2 is -1. All right, so left and right side are not balanced by charge. So there's a reason for this. It is balanced by mass, but not balanced by charge. Now the goal here today is to be able to fix that and maybe throw in a coefficient or two to make things work. So a redox reaction can be separated into their different half reactions. We will write oxidation states, then identify the species that are being oxidized and reduced, like you have done in your previous lessons. You will separate them into 2 different half reactions. One would be the oxidation half reaction, and one would be the reduction half reaction. So let's take a look at a general equation here, our overall reaction. A plus B yields A plus B minus. Now, since A had its charge going up and B had its charge reduced, that means B is the reduction and then A is the oxidation. So we split those up right here. Now, you'll notice that for oxidation ones, the electron is on the right side. That's because oxidation is the loss of electrons. You remember oil rig, oxidation is loss, and reduction is gain. That's the rig, R-I-G. Reduction is gain of electrons. So that is the way it will always be in any type of half reaction. Oxidation ones have the electrons on the right, reduction ones have the electrons on the left. So these two are what's considered your half reactions. Okay, we've split them up. Now, being able to do that is the key part here, and then you're able to balance them once you've split them into that. So step 1 is to separate them into their half reactions. So in our original example, we've taken Na plus Cl2, and Na plus and 2Cl minus. Now Na, or sodium, has oxidized. It has gone from a 0 to a +1 charge. So that means it has lost 1 electron. And then Cl2 has actually picked up 2 electrons. It has gained 2 electrons to make 2Cl. Okay? So then now what you're going to do for step 2 is to make the number of electrons equal or multiply by some type of factor. Now we could see here that we had 1 electron here for that 1, and then we had 2 electrons here. Well, we need to make those number of electrons the same. So what we needed to do is we needed to multiply this number 1 by 2. So we multiply this by 2, but we have to multiply all of them by 2. We have to distribute that 2. So therefore, we end up with 2 Na plus 2 Na plus 2 electrons. Now our electrons are balanced on each side, and now we can smush those half reactions back together to bring you your full reaction. Now we can write the complete reaction here, and what you'll do is eventually you will cancel out your electrons on both sides and then end up with your final reaction. Okay? Yeah, cancel them out. Pretty simple stuff. We'll walk through some examples. I think you'll be able to get it. It is not very difficult. So just to note, this is the easy part. This can only be done for reactions that contain oxygen or hydrogen, that do not contain oxygen or hydrogen. Unfortunately, reactions such as those are outside of the scope of this course and will be covered in your advanced chemistry class, either AP or IB chemistry. So below, this reaction is actually a balanced reaction by mass and charge. The reason why it's making it balanced right here is you had to add in a water. Actually, you had to add in the H plus here, and it's in acidic conditions, and you had to add in the water. That's what's making it balanced, and there's a little trick to it. So, but you'll worry about that in your next chemistry class. So this method is called the tie method. I like to call it the tie method, where you will just quickly balance them. And this is what it will look like. You just draw in ties, and you'll show your different half reactions, and it make it quite easy to see. Okay, so this is where we're going to get to. So let's try an example here. You have iron as a solid, and this is copper 2 plus, so this would be aqueous copper because it has an ion. And this would be aqueous copper again, and this would be aqueous iron. So we left off state symbols here, but these would all be aqueous since they're ions. Anyways, enough of the distraction. So what we would do is we would first tie in our atoms. Like goes with like, so iron goes to iron, and then copper goes to copper. Now for the iron one, iron has changed from Fe to Fe3 plus, and so that means that it has given away 3 electrons. Okay. Now, one way to think about this is you had 3 negative charges plus 3 positive charges here will equal 0, right? And that's what we want to be. This is a 0 charge. So these electrons are kind of canceling out this ion. Maybe that's one way to think about it. Or you could identify that this charge went up, so that was the oxidation part, and we know that oxidations have electrons on the right because oxidation is lost. And then so here's your reduction. This is copper 2 plus, and it's gaining 1 electron and going into copper plus. So now your factor here is going to be a 3 because you have 3 electrons here, and then you have 1 electron here. Well, we need this electron to be a 3 to balance all the electrons out. So we're going to multiply the whole thing by 3. And then we'll put coefficients in there as to symbolize that. And then you are done. That is your balanced redox reaction. Okay, quite simple. Take a look at this one. This one is also balanced by mass, but not by charge. You will draw in your copper, and we know that that is copper. The charge is increased, so it is oxidation, which means the electrons are on the right side. And then you'll draw in your silver, and the charge has now decreased, so that charge has been reduced, so it is a reduction reaction. Now you'll notice the electrons here. You have 1 electron and you have 2 electrons. So we need to make this one a 2. We need to turn this into 2 electrons. So we're going to multiply the whole thing by 2. And so that means that we are going to have 2 silvers, 2 silver pluses, and 2 silvers here. Okay, so now it is all balanced by mass and charge. Okie dokie. And this should be our last one. We have aluminum and we have nickel 2 plus reacts to form aluminum 3 plus and nickel solid. So you will tie in your aluminum, and that's an increase in charge, so that is an oxidation. Okay, the one that has an increase in charge is oxidation, and so we write the electrons on the right, and then we have our nickel. Then as a reduction in charge, so it's our reduction reaction. It is a gain of electrons, so the electrons are on the left side. And so we have 2 electrons here, and we have 3 electrons here. Well, these need to equal each other. They need to be the same. So the least common multiple of those is actually going to be 6. So we need to turn this 2 into a 6. We need to turn the 3 into a 6. So we're going to multiply this 3 by 2. And we're going to multiply this 2 by 3. And we'll get that. All right. So your final balanced redox reaction would look like that. So this is pretty much what your test will look like. I'll ask you what are the coefficients for all of these, and it should be pretty good. All right. I hope you hope you learned something, and have a great day.